Good evening. I'm Calvin Joseph, and today I'll conduct your week 4 problem solving and doubt clearing session for the course Digital Electronic Circuits. So today there are various topics which was covered in Sir's class, the sessions, and we will look into it. And we will also solve some sums. So week 4, Sir has touched about multiplexer. Then Sir has talked about demultiplexer. Then what is a decoder, encoder. Further, Sir has talked about parity. What is the need of parity and how do we check parity, etc. Okay. So we'll start with the first thing, that is the multiplexer. So this is a block diagram of multiplexer. You have 0 and 1. It has a select line. Let us say select line. This is your Y. And these are your two inputs, A and B. Okay. So can you tell me what is the truth table of a multiplexer?
So S0 is, if S0 is 0, it should select A. If S0 is 1, then it should select B.
Okay. So what is the logical expression for this? Any way to logically express this as? You're right. What you told is right. We can also write Y is S0 bar A plus S0 and B, right?
S0 B, yeah.
So this is one expression. Like multiplexer makes sense when you look at it visually, but then in certain cases you need to find a logical expressions, then you'll have to use this format. Okay. So this is a 2:1 multiplexer. That is, from two inputs, I am getting one output. Okay. Now, can I make a 4:1 multiplexer from this? So, okay, let us see, consider 4:1 multiplexer. You'll have two select lines in that case. So you'll have S1, select line S1, select line S0. You'll have three inputs. Let us say four inputs, A, B, C, D, and this is your Y. Okay. So again, as you have told, the truth table is S1, S0, and Y. So depending on the state of the select line, which state, which condition it is, the output will either be a signal at input A or signal at input B, C, or D. Okay. So it is basically selecting which signal you want to pass it to the further circuit. Okay. So that is the goal of a multiplexer. So this is a 4:1 multiplexer. Okay. What do you think would be a possible application of a multiplexer?
Yeah, time multiplex, like if we want to have a particular channel to be on for a time, we have to give the logic accordingly, and this channel will be selected. Likewise, we can use this application.
Yes. Like you have many possible configurations. Let me give a example which I was just thought about. Like you would have used a microcontroller. Okay, there is a microcontroller. It would be something like this. Like this, there'll be many pins over here, many pins over here, many pins will be there. Okay, so this is your MCU. Now the microcontroller has various things. It will have uh, some pins for VDD, some pins connected to ground. Okay. Here also there will be a pin for VDD, ground, VDD, ground. Okay. Various things are there. Various pins are there. Okay, so there are pins for power and there are pins for ground. Then there are certain pins. Let us consider this pin. Okay, this pin. This pin is a, let us give it a name, pin. Let's give it a name, pin E. Okay, this pin has a name E. Now this pin, what is the use of this pin? What purpose it can be used? So you would have used a microcontroller. Like what things can you do using a microcontroller? Any idea?
Like we can have uh, uh, like input output pin
Yes.
or PWM
Yes.
or timers.
Okay. Okay. So you are very right. So you can use it as a GPIO. You can use it as a PWM. You can use it even as a timer pin. Or there are various. You can use it as a pin also. Analog pin. You could use it for serial communication also. Various possibilities are there. Okay. So what the microcontroller manufacturers do is that pin E could be used for many possibilities. It could be used as a GPIO, it could be used as a PWM, it could be used as a timer, it could be used as an ADC input, it could be used for serial communication. It could have multiple purposes. So that means at one physical point, we are giving a provision for it to be used for multiple purposes. But does it mean that at a time it will both do GPIO, PWM, timer? Can it do the same thing at the same time? No. So it will not be able to do the same thing at the same time. So what we do is it is known as pin multiplexing. So at a time we either use it as a GPIO pin or we configure it to be used as a PWM pin or as an ADC pin. Okay, there are various possibilities. So that is some internal thing. So just one small application where you use the concept of multiplexing. Okay, this is known as pin multiplexing. Okay, so this is a multiplexer for multiplexer. Then we, so there is in a multiplexer, what do we have? We have a sort of if else statement. Okay, the if else statement is used a whole lot in your C language, in your C++, if else, etc. But the multiplexer is a logical realization of the if else statement. Okay, if else statement, or there is also something known as use case. You say case A, case B, case C, etc. So the multiplexer is a sort of digital equivalent of those things. Okay. Also, there is a pin known as a strobe pin. Okay. This strobe pin is kind of like an enable pin. If this pin is high or if it is in the active mode, then your multiplexer will work. It will give the desired output, else it will not give the desired output. Okay. So now, after you have a multiplexer, you have also something known as a demultiplexer. Demultiplexer. So it is the opposite. So you have an input D. Depending on 0, could be 0, 1, and this your select line S0. It could go to output Y0 or Y1. All right. So this is your select line S0. These are your outputs Y0 and Y1. If your select line S0 is 0, Y0 is the getting the signal D and Y1 is at 0. Your select line is 1, then Y0 will take the output 0 and Y1 will take the output D. Okay. So this is like we are either connecting it here or we are either connecting it here. So that is what is a demultiplexer. So this is a 2:1 demultiplexer. Okay. Suppose I want to, sorry, not 2:1, 1:2. So 1:2 demultiplexer. Can we have a 1:16 demultiplexer? Is it possible? Okay. Okay, so it is, let's say, assume it is possible. So how do we do that? So we have the input will be over here. The input pin will be over here. And these are the pins. Okay, this will be Y0, Y1, dot, 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 all the way to Y14, Y15, and so on. Now, in this case, we need to have 4 select lines. Okay, 4 select lines. That is your S3, S2, S1, S0. Okay, so depending on which select line, so what Y0 is? Y0 is when all the select lines are 0. Y1 is when only S0 is 1. Y15 is when all are on, all are high. Okay, so this is how you can, what you can do is you can steer the input from here to here, or from here to here, or from here to here, or from here to here. Okay, so demultiplexer is opposite to a multiplexer. It is taking, demultiplexer takes one input and it can connect it to multiple outputs, connect it to different outputs, but it will connect only one at a time. Multiplexer is the opposite. It takes multiple inputs and only passes on one of the inputs to the output, depending on the select lines which are set. Okay. So that is the concept of multiplexer, demultiplexer. Is there any doubts till this part?
No.
Okay. Now, what we can have is, there's something known as a decoder. Okay, we have a decoder. So what a decoder does, for example, let's say this is a 3 to 8 decoder based on the select lines. Let us go with a simple example. Okay, we'll proceed with this. So this is 3 to 8 decoder. We will have Y0, Y1, Y2, dot, 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 Y7. Okay, so depending on these lines, your Y0, Y1, Y2 will show some output. It will show some output. What we will do is, we may want the logical equivalent. That is, if this Y, let us say this is your A, B, and C. Okay, these are your A, B, and C. So we may want, depending on what combination of A, B, and C, we can get, sort of min term. You can say Y0, Y1, Y2. We can OR them. Like this is a function min term of 0, 1, and 2. This is one possible. So we can have like this configuration. Then if it is taking from here, taking from here, taking from here, and you can OR it, then this is what 1, let's say 4, let us say 6. So what it will do is, if when this possible configuration is there, it will give our output high. So it will check whether such a thing, such a bit pattern has occurred or not. Okay, so that is a function of a decoder. right? Okay. So can you give an example of a decoder which you guys have studied or which you guys have used?
Like in a motor to have a speed, we will be having that step decoder. That is one example.
Okay.
Keyboard encoder. Like if you press a key and it will sense the frequency and it will give the output of that keyboard to a monitor or a memory like this.
Okay, yes, yes. That is, you have pressed something and it will like analyze like which one have you pressed and all that, right?
Yeah, same.
Based on that. Okay. Hmm. So now, have you heard of the binary to decimal decoder?
Yeah.
So binary coded BCD decoder also is there. So there can be a binary BCD to decimal decoder is there. Also, you have something. This is known as a segment display. Right, where this is like how it looks. You have this here. So this is your segment A, B, C, D, E, F, G. Okay. So now, if you want 0, okay, what should glow? This should glow, 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 this should glow. Okay. So for 0, it is actually what? Summation of M, A, B, C, D, E, F. Okay. If you want your 2, you want this. So that 2 is your summation of M, A, B, D, E, and G. Sorry, G. Okay. So this also is a kind of decoder where you have certain inputs. Accordingly, you will generate what should be your A, what should be your B, etc., such that your LED will display the correct output. Okay. So this is your decoder stuff. Okay. We'll consider something known as parity. Okay. So sir has talked. Let us say there is a stream of bits. So you have told that you can have an encoder decoder. That is when the keyboard, you will press a key. Okay. You press a key. Accordingly, it will generate some ASCII format of that. It is a set of bits. Okay. It is a set of bits are generated. Now, let us say those bits are, let us say that is 0, 0, 1, 0, 1, 1, 0, 1. Okay. These are the set of bits. These bits have to be transmitted. Okay. You are transmitting it. Now, over here, you have a receiver. Okay. What receiver will do? It will store these bits. Okay, it will store 0, 0, 1, 0, 1, 1, 0, 1. Now, how does a receiver know that your bits are correct? That the bits which it has received has not been corrupted by noise. How can it be sure that it has not been corrupted by noise? Okay. So there is a concept known as parity. So here what they do is they count the number of ones. So how many ones does this set of bits have?
4 ones.
4 1. So is it odd or even?
Even.
Yes, so it is even. So what the receiver will do, that also will count whether the number of bits it has received, the number of ones, whether it is even or odd. Okay, whether it is even or odd, it will check. Okay. Now, the advantage of digital. Okay, why many times we are going from analog to digital? Why do we go to digital concept? Why is digital communication, digital circuits, digital electronics, why is it very useful? Like sir had told, as sir had mentioned in the first week, that they have good noise margin, right? They have a better noise margin, more tolerance, and like you have a resistor, you have a capacitor. After some time, you know that resistor value will change, capacitor value will change. But the advantage of digital is you have a register, that register values will not change, right? You have programmed it, it is this value, means it will be this value. It can store for long periods of time, etc. So there are many advantages of it, of digital technology, and so you guys are also studying it. Now, when you're transmitting set of bits, you need to know whether the bits have been transmitted correctly or not. So for that, you check whether the parity of the bits sent at the transmitter side is same as the parity of the bits sent at the receiver side. And there is a lot of maths and which people have checked and which people have found out that the usually only one bit would change. Only one bit could go wrong. One bit could go corrupted. That is most likely. And the likelihood that two bits at a time got wrong is not that high. Okay, that likelihood that two bits at a time could go wrong is not that high. So there is a very funny story which I read long back was like this story I read when I was reading studying about probability and everything. So there is a man who used to travel by plane. Okay, he used to travel by plane. He used to probably read the news a lot, and he saw that bombs are kept in the plane crashes, there was a suicide bomber or something. Like many things he had read. So he was very scared. So what he had studied in probability is that the probability of an aeroplane having two bombs is zero. Okay, the probability of an aeroplane having two bombs is zero. So what he used to do is he used to take one bomb with him. Okay, with him he will have one bomb, he will take it and go, and then he will be happy that my bomb will not burst. Okay, he is confident that his bomb will not burst. And so, because he has taken one bomb into a plane and there will not be a second bomb, so there will not be a bomb by another terrorist. Okay, so that is the logic he kind of used to know to give him that kind of assurance or confidence that he will not die by a plane crash due to a bomb. Okay, so that is the logic. So it is a very funny kind of story or everything, but it is similar. So what we are doing in parity is we are checking that whether the parity of the bits being sent is same as the parity of the bits not being sent or bits being received. Okay. Now, in this case, so let us say our thing is working in the concept of even parity. Hmm? That means the bits which we send should have even number of ones. But we have, let us say this, like we have 8 bits, right? It is 1 0 1 1 0 0 0 1. But what if happened is the information which we want to send actually has 1 0 1 1 0 0, but it has a 1 here and a 1 here. Okay, this is the information which is correct. This is the information which we need to send. So now what should we do? We cannot change this information because this information is correct. This information is correct. This is the stream of bits which carries some particular information, and this information has to be sent. But the problem is it doesn't follow the law. It is not even parity. So what is done in such a case? what is done? They send what is known as a parity bit. There is something known as a parity bit. This like an additional bit is sent. So in this case, there is even parity. Even parity is already there. So the parity bit, you set it as 0. But in this case, since there is odd parity, what you do is to make sure you get even parity, you add up the parity bit you set as 1. So then when you will see the overall data when you will see, it will appear to have even parity. Okay. It will appear to have even parity. So this is the concept of parity and how you, even though your data may not have the parity which you want, you can generate an additional bit. You use an additional bit to change the parity so that your whatever data you are sending overall, that is either even parity or odd parity. Okay. So we'll start with some assignment questions. These are some previous year assignment questions. So how many 2:1 multiplexers are required to generate a 256:1 multiplexer? Okay. Okay, so what they have given us is there is a 2:1 multiplexer. Okay. You have your input x1, you have your input x2, and this is your output y. You have to use many combination of this 2:1 mux. Okay. And you have to generate a 256:1 mux. Okay, so when you have these, large size numbers which you need to consider and check, what I'd recommend is first from a 2:1 mux, how do you make using 2:1 mux? How can you generate a 4:1 mux? First, you try to generate a 4:1 mux. How will that look? Can anyone tell me?
Two numbers of 2 to 1, and one will be having S0 as input and as the select line, and another one is having S1 as line.
Okay, so this, I think this is your S1. This will be your S1. This will be your S0. This will be your S0. So this is your X0, X1, right? X2, X3. This goes over here. This goes over here. This is the output Y. Okay. So, to say, so it is very clear. Sorry. This is S1. Right? You have S0, you have S1. S1 and S0. So this is 0, 0, 0, 1, 1, 0, 1, 1. So what is your Y? When S0 is 0, that is this or this. And when S1 is 0, that means it will take from here. So this is X0. Similarly, you can get X1, X2, X3. So now when I've gone from a 4 to 1 mux, how many 2:1 muxes I needed? How many 2:1 mux I needed?
3.
3. Yes, you needed 3 2:1 mux, right? So this can, how you can write this? This is 2 raised to 2 minus 1. 2 raised to 2 minus 1. So you want a And this is what 4 minus 1, right? So you want a 256 to 1 mux. So that means the number of 2:1 muxes you need would be some 2 raised to it would actually be your 256 minus 1. So that actually is your 255. You require 255 2:1 muxes to generate one 256:1 mux. Okay. Is this clear or you want me to repeat it?
No.
Okay, okay.
Clear.
Okay. We'll go to the next question. So, what are the number of select lines required in a 1:8192 demux? Okay, so we have, how does this look? This is an input, right? It has y0, y1, dot, 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 such a large value, y8191, right? So, and this it will have select line S0, S1 till S something, that which we need to know. So, how many select lines are needed? Which of these options do you think is correct? Because what I want you to do is for a 2:1 demux, how many select lines do you need? Let us say make a table. So we have a demux configuration and a select
Only
line.
one.
So if you have a 1:2 demux, you need only one select line. If you have 1:4 demux, you need two select lines. If you need 1:8 demux, you need three select lines. So if you will see the pattern, what the number of select lines is log of 2 to the demux configuration, to the demux amount, right? So in our case, it would be log to the base 2 of 8192. So what is that value? Okay, you guys, I also don't have a calculator. So as you are studying digital circuits, you need to know the multiples of 2 very well. Okay, so that is powers of 2. This is important from n. So 1 power means it is 2, 2 means 4, 3 means 8, 4 means 16, 5 means 32, 6 means 64. Okay, how it scales, 64. This is 128. This is 256. This is 52. This is 1024. 11 is 2048. 12 is 4096. And 13 is 8192. Okay. So what does this mean? So 2 raised to 13 is 8192. So if you do log to the base 2 of 2 raised to 13, that is log to the base 2 of 8192, what would happen? This would turn to be 13 into log of 2 to the base 2. That is 13 into 1. Okay. So the number of select lines which you need is 13. Is it fine?
Yes.
Okay. Okay, so I just told some little bit of maths, which is like a very basic things which you can soon remember and keep it stored. So it'll be handy. At a flash, you'll be able to get the answer. Hmm. Okay. So you have to find the canonical POS expression of y for the given figure. Okay, let us see this question. Okay. So now we have to first find the product of sums. And let us see this circuit. So you know for a 4:1 marks, what is the truth table? It is, if you see over here, it is A and it is, okay, let us draw a 4:1 table. So you have 0, 0, 0, 1, 1, 0, 1, 1. This is your select lines, that is your A and B. This is your I0, I1, I2, and I3, and this is your Y. So your Y is actually what? A bar and B bar and I0 plus A bar and B into I1 plus A and B bar and I2 plus A and B and I3. Okay, so this is the logical equivalent of a 4:1 mux. Okay, very good. This is simple. Now what you will see, what is our I0? I0 is C. So Y is A bar and B bar and C. Okay. What is I1? I1 is D. So A bar and B and D. Okay, so the meeting will end in 1 minute. So I will restart the same meeting. So you have to join on the same link. Don't worry, you have to join on the same link. This because I don't have the premium version of Zoom, there is a 40-minute limit. So after this 40 minutes finishes, it is in the last minute, it will finish. Then the meeting will automatically end. I will restart the meeting with the same link. So you don't have to worry. You have to just join using the same previous link. All right. Okay. So we'll proceed. Now A and B bar and I2. And what is your I2 given as? I2 is C bar. So it is A and B bar and C bar. Then what is I3? I3 is C bar and B bar. So that is equal to A, B, sorry. So what is our I2? It is, if you will notice carefully, it is C bar and D bar. Okay, C bar and D bar. So that is why it is A, B, and C bar and D bar. Okay, so this is how we write our logical expression. So now, let me go to the next page. What is Y? Again, I'll write it down. Y is A bar and B bar and C plus A bar and B and D plus A and B bar and C bar plus A, B, C bar and D bar. Okay. Now, let's draw the K map of this, right? So you have A, B, C, D, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, and 1, 0. Okay. Fine. This is the K map. Okay. So you have to use K maps. You have to be very proficient with it. There's no escaping of it if you're doing this course, right? So here again we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so we will start the first configuration. What is the first configuration? A bar and B bar. And oh, let us start with this. Let's start with this. So you have A and B and C bar and D bar. So that means you have A and B and you have C bar and D bar. So that is your 1. Okay, this is your 1. If you will see, this is the sum of product. Okay, the sum of product. So we will first analyze in terms of sum of product and then we will get the product of sums. They can be interchanged. We will see how. So first thing is A, B and C bar and D bar. So A, B is 1, 1. C bar and D bar means 0, 0. So this is 1. So when all 4 variables are there, that means the size of your K-map is 1. So if there are only 3 variables, that is in this case, the size of your K-map should be 2. Okay, so how will we do it? So A bar and B bar means 0, 0. So A bar and B bar. And C means C is 1. So that means C is 1 and C is 1. So that means this is your 1 and 1. So that corresponds to A bar and B bar and C. Now let us try our A bar and B and D. So we have A bar and B. So A is 0, B is 1 and D. So D is 1 corresponds to which case? That is you have your D is here, D is here. So that means 1, 1 will be this is 1, this is your 1. Okay. Now the last thing which is left for us to do is A and B bar and C. So A is 1, B bar is 0 and you need to get C bar. C bar is which case this 0, this 0. So you get 1 and 1. Okay, so this is your K map which you got. So this is for sum of product. But in the question they asked you for, you wanted product of sum. So what is it? You have to do very simply what you have to do. Wherever it is 1, 1, the other places will be 0, 0. So it is 0 here, 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 0 here. So your actual output Y is the product. This is a symbol for product. Maxterm, that is your 0 is there, your 1 is there, 4 is there, 6 is there, 10 is there, 11 is there, 13 is there, 14 is there, and 15 is there. Okay, so this is how you must analyze this question. Okay. So basically they told us to find the POS expression for the figure. They gave a 4:1 marks and they told us you find what is the overall logical expression of that. So one by one, step by step, we broke down the expression of a mux. What is the logical expression of a 4:1 mux for different inputs? Then we put the what inputs we are applying that we added. And then since we have written in terms in the SOP, we drew the K map, we filled it with your 1, 1, 1, 1 wherever required. And then since we needed it in terms of POS, whatever was 0, 0, that is the product of max terms. Okay. Okay, so I'll proceed to the next question. Proceed. So this is a pin configuration of an IC. A is 0, B equal to 0, C equal to 0. So how will this IC function? Okay, let us look into it. They have told in this circuit, they have mentioned that A is equal to 0, B is equal to 0, and C equal to 0. So what does it mean? So now you see in these ICs, there are these bubbles. What do these bubbles mean? What does those bubbles signify? Why do I add suddenly a bubble for the input and output? Hmm?
It's not gate.
Not gate could be a skins, but it's mainly to signify that it is active low. That is, if your output is at Y31,
Yes, it is active low.
means
Hmm.
it is 0. Correct. So it is active low. Now, in case of now there is something known as a strobe pin. Okay, there's a strobe pin. Strobe pin, as I told earlier, it is like an enable pin. And if you see the strobe pin, it has a 0, means it has a bubble. So strobe, which is like an enable pin, is active low. It is active low. It means when the input to the strobe pin is 0, that means that IC is active. So here we have A is equal to 0. That means over here to this strobe pin it is 0 and to this strobe pin it is 1. So tell me which of the ICs is active, the top one or the bottom one? Which IC is active? Okay, I'll repeat myself. There is a strobe pin in the IC. Strobe pin is like an enable pin. Enable pin means if it is active. If enable pin is active means that IC will work. If the enable pin is not active, the IC will not work. That is the objective of your strobe pin. Now, because there is a bubble in front of the strobe pin, it means that pin, input pin is active low. Means when you give an input of 0 or low input to that pin, then your IC will work. Okay, so as you see, the pin A is connected to the strobe pin for your both IC1 and IC2, it is connected by a NOT gate. So since A is 0, for the first IC, your strobe pin is connected to 0. But for the second IC, it is connected to 1. So as the strobe pin is 0, this IC will function because it is enabled. Okay, it has been enabled. Now, they have also told that B equal to 0, C equal to 0. That means B is 0, C is 0. So this now we don't need to consider because it is not active. So B is 0, C is 0. Now, B, C, D, E, they are B, C, D, E, they are active high. Okay, they are active high. So now, if you will draw the truth table of this IC, you have B, you have C, you have D, you have E. How do you write the truth table? That is 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. Output is what? Y0, Y1, Y2, Y3, and so on. So in our case, we are only interested in this part, right? Because what we have B equal to 0, C equal to 0, that is this part of the truth table. So the possible places where the output could get connected is between Y0 to Y4. Okay. So this is basically acting like a demux from Y0 to Y3. Okay, it is acting like a demux from Y0 to Y3. All right.
Yes.
Okay. Okay. So now we proceed. Okay. We have to do this question. Okay. So the output Q over here, actually this is looking small. So the output Q over here should be A or B or C. Okay, that is the output we desire. Now we are given a 4:1 mux. There's a 4:1 mux. A is MSB, C is LSB. They are telling to use A and B as select lines. So this is A, this is B. So these are the select lines. C is an input variable. That is, we can consider this could be C, this could be C, this could be C bar, this could be 1, something like that. Some configuration we have for the inputs. Okay, some configuration for the, are possible for the inputs, and that is what we need to find out. Okay, that is what we need to find out. So how will we do this part? We know the output is A or B or C. Let us see the output of the Q. What is Q? Actually, it is A, uh, A bar and B bar and D0 plus A bar and B D1 plus A and B bar D2 plus A B D3. Right? This is your output Q. Now we need to see which D0, which D1 and which D2, D3 can get us the required output A or B or C. So if you will notice, they have given for all the cases, D3 is 1. Okay, we have D3 is 1. They have also put D2 is 1. So very simple, they are making life simple. So this is you have A bar and B bar and D0 plus A bar and B and D1 plus A B bar plus A B, which if you further simplify, it is A bar and B bar and D0 plus A bar and B D1 plus A. Okay. Hmm. Okay. Achha, I have made it a very complicated. I'm sorry, let me go through a different method. So we have a 4:1 mux, right? What is the 4:1 mux? This is A, this is B, this is your output Y. So this is 0, 0, 0, 1, 1, 0, 1, 1. This is your D0, this is your D1, this is your D2, and this is your D3. So your output Y in terms of min terms, if you write output Y in terms of min terms, it is what we had earlier discussed. It is A bar, B bar, D0 plus A, B bar, D1 plus A bar, B, D2 plus A, B, D3. But if you write in terms of max terms, how will it look? If you write in terms of max terms, then how will your output look? Y be equal to A or B or D0 and A or B bar or D1 and A bar or B or D2 and A bar or B bar or D3. Okay. So what do we want? Our output Y, we want it to be A or B or C. So what we should write? Our D0 should be equal to C. And we require our D1 and D2 and D3 to be equal to 1. Okay. You may ask me why. Why do I say that they should be equal to 1? If you have X, anything X, it could be A plus B, AP bar, AC bar, anything. X or 1, the output is always 1. Okay, so if I say D1 equal to 1, D2 equal to 1, D3 equal to 1, then this term, this overall term will become 1, this overall term will become 1, this overall term will become 1. So then my output y, will be what? A or B or C and of 1, and of 1, and of 1, which is actually equal to A or B or C. Okay, so that is the logic. Okay, so let's proceed to the next question then. So you tell me which of the following statements are not true. Which of these statements do you think are not true? So you guys, I don't know whether all of you are studying, teaching. Exactly, I don't know properly about you, but you have enrolled for this course, Digital Electronic Circuits. You might be giving the exam. So when you are giving exams, there is a common enemy which many students have, that is known as silly mistakes. Okay, we make what is known as silly mistakes. And why do we make a silly mistake? Because we don't read the question properly. We don't read the question properly. So I want you to read the question properly. It says, which of the following statements are not true? Okay, which of the following statements are not true? So they have given one, two, three, four. Four statements they have given. Okay. This kind of questions is like a sort of logical reasoning questions, which you would also come across when you're giving your placement exams and tests to join companies, everything. And there, that speed is the main concept. You need to do very fast and everything. So you have to first read the question properly. You have to understand it very well. Then you have to solve it. So what is the tactic which many people use is they will write the important parts of the question. You read the question. As you're reading the question, you write the important parts of the question, so that you don't need to again go and read the question again, because reading the question again will waste your time, right? It will waste your time. So instead, you just write the main parts, main important crucial information of the questions which you need to focus on, and then you try to find the answer. Okay, so that's just a simple thing for you when you will be giving your placement exams. Even in GATE exam, this logical reasoning, everything is there. So I just want you to be prepared. So what they have told us, what statements are not true. So their statements can either be true or it could be false. Okay, statement can either be true or false. Okay. So for more than two input X NOR gates, output is 1 if there are odd number of ones at input. Okay. This is difficult question, difficult statement, and on the spot you will not know whether it is right or wrong. Let us ignore it for the time being. We'll ignore it. Okay. We'll go to the next question. Even parity refers to the presence of even number of ones in bit patterns, and odd parity refers to odd number of ones. Is this statement true or false?
True.
True. Okay. So 2. Parity generation and check involves single input XOR gate circuit. Is that true or false?
It is XR only, but it is not a single input. I
Okay.
think so.
Yes, so that is a false. So it is 3. Parity check is useful in detection of errors when a group of bits is transmitted. Is it true or false?
Yes.
So it is true.
Yes.
So your 2 and 4 is true. They have asked what statements are not true, right? So that means, and if you see the options, there are two options each. So that means 3 is false. So yeah, 3 is here is false, 3 is here is false. Only thing we don't know about 1. Okay, so 2 and 4 we already know it is true. So false be 3 and 1. Okay, 3 and 1. And if you will go and actually do this thing about the 2 input XNOR gates and more than 2 input XNOR gates, you'll find out it is false. Okay, so that's why the answer is D. So reading the question carefully is very important. Doing it quickly, writing the crucial points of your question also is very useful. And it is useful not only in this digital electronic circuits, it will be useful in your logical reasoning, aptitude, gate exam, various other exams. All right. Okay. So let us see, realize the following expression using a 4:1 multiplexer where C, D are the select lines. Okay, they really like 4:1 multiplexers. It is something which they really enjoy and like. So let us look into this circuit. Mhm. So okay, so now let us see. So we have a 4:1 mux. We have a single output Y. You have 0, 0, 0, 1, 1, 0, 1, 1. And what are the select lines? You have C is the select line, D is the select line. So you have your input I0 here, input I1 here, I2 here, I3 here. So you need to find out I0, I1, I2, I3. You have to find out many things. They have given you what is the max term representation of this. So now we have to draw the K-map. K-map is something which you can't escape. I'm again repeatedly telling you. So let us draw the K-map. We have the K-map. You have A, B, C, and D. Okay. You have your 0, 0 here, 0, 1 here, 1, 1, 1, 0 here, 0, 0, 0, 1, 1, 1, 1, 0. Okay. This is what 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So now they have given 4, 8, 9, 10, 11, and 14. So we have 4. Okay. Sorry. And then there's a max term, right? So it'll be 0. So 4, then 8, 9, 10, 11, and 14. Okay, we have got these whole set of zeros. So what will be your 1? This will be your 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay, this is your 1, 1, 1. Now, how can we analyze this? Now, if you look at this part, okay, if you look at this is your C and D, right? So CD, which corresponds to 0, 0, that is this part. That is this part, right? When you check your 0, 1, that is for this row, this column. When you're checking for 1, 0, that is for this column, this column. in which when you're checking for 1, 1, that is for this column. Okay? It is for this column. So that means this will correspond to your I0. Okay. This will correspond to your I0. This will correspond to your I1. This will correspond to your I2. And this will correspond to your I3. So now if you see the columns, if you will see the column carefully, you will observe two columns are the same. Which two columns are the same?
I1 and I3.
Okay, so we have got what we have got. We have got I1. Okay. We've got I1. This is equal to I3. Very nice. So that means what options are we left with? We're left with this option and this option. Now we'll look at I2. Okay, let us look at I2. We'll look at I2. So I2 has 1, 1, 0, 0. So if you see A, B, and I, so you have 0, 0 here, 0, 1 here, you have 1, 0, and this is the truth table. Let us look at the truth table. So if AP is 0, 0, that is this case, what is your I2 is 1. If AB is 0, 1, that is this case, what is your I2 is 1. All other cases, it is 0, 0, right? So if you look carefully, your I2 is actually equal to A bar. Your I2 is equal to A bar, right? If you see,
Yes.
so we have got what we got. We got our I2 is equal to A bar. A bar. So that means this we got, this we got. Now, just for to feel happy, let us try to find out what is I0. Let us try to find out what is I1. So what is I0? I0 is this one. There are two over here. I0 is this and it is this, right? So I0 actually corresponds to what case? A bar and B bar, this case, plus A and B, which is this case. So this is our I0. And if you see this A bar, B bar plus AB. Okay. And now if we want to find out our I1, what is our I1? That is equal to this one. So that is what? A bar and B bar. Then this one, that is what? A bar and B. Then this one, it is plus AB. So this is our I1. Okay, so in this manner, we got what we got. We got our I0, we got our I1, we got our I3 because I3 is equal to I1, and also we got our I2. Okay, so this is a very interesting question. Very like intuitive. You have to think in a way to solve it. Okay.
Yes.
So now we'll go to this question. So what does this circuit represent? Can anyone tell me? What does this circuit represent?
8 is to 1
Yes, so it is
multiplex.
8:1 mux. Okay. So now they told the output F is A or B and C. Again, we have to use the K map. Very, very simple. we have to use the K-map. So we have A, B, C. So this is A0, this is A1, this is 0, 0, 0, 1, 1, 1, 1, 0. Let us make it like this, right? You have your 0, 1, 2, 3, 4, 5, 6, 7. Okay. Sorry. So now let's go step by step. So we have B and C. B and C. That means B is 1, C is 1. So that means this is 1, 1. Next we have A. Means whatever is in the column of A, that is 1. So that is, means this is 1, this is 1, and this is 1. Okay. So this is our logic. This is the K-map. Now we have to assign what should be our D9, D1, D2, D3, D4, D5, etc. So how will you assign those bits to it? Such that you get the output F equal to A plus BC. Right? That means when A is 0, okay, and you have B is 1 and C is 1, that is in this case, that is this I'm talking about this case, then here you have output 1. Then in all other cases where A is 0 and B is some other value, you will get the output 0, 0, 0. And in the case where A is 1, that is in this case where A is 1, all have to be 1. So this is 1, 1, 1, 1. Okay. So this is how you can set the bits. This is how you can put the bits. What bit should be where?
Can you please repeat this?
Okay, I'll repeat it. So first, I drew the K-map. K-map is a simple representation of this logic.
Yes.
I have this one. Okay, this one. This happens. This is single one. Otherwise, for this I can group it together, sort of way. So this one is there. This bit is 1 when my A is 0. A is 0. Now my B in this case is 1. So means I have to go from here. I'm going here. Now my C also is 1. So I'm going here. Right? So that means this bit. So this bit D3 should be 1. D3 is 1. Now my A is 0. But I have another 3 more cases. And if I see the K-map in all the other 3 cases, it is what? 0, 0, 0. So that means all the other bits are 0. So I have to put this 0, 0, and 0. Right? Then I go to the next case where what I have A is 1. A is 1. And if you will see the truth table where A is 1, all are 1, 1, 1, 1. That means all should be 1, 1, 1, 1. Thus, I can write down what should be the bit set as such that I can get this logical expression. Okay, any queries in this? You want me to repeat it again?
No.
So I'm sharing the link to my YouTube channel and to the link where the notes will be posted. So this will be this meeting which is being recorded. It will finally be posted on YouTube after editing, etc. And then you can access this video. Also, these notes which I have handwritten notes also will be uploaded on the Drive link where you can access it from there as well. All right. Okay. So now we'll proceed for the next question. Over here. Okay. So let us see, you have your x3, x2, x1, x0. If the input to the circuit x3, x2, x1, x0 are in 8421 BCD numbers, then the output y3, y2, y1, y0 are in which of the following options? You consider y3, y2, y1, y0 as output of OR gates whose inputs is given by cross sign. Okay. So this is a question. Let us also take the screenshot of the options side by side. Okay, this meeting will end in 1 minute. Once the meeting ends, I will restart the meeting with the same link. You can join in the same link as well. Okay, so they are saying the inputs are 8421 BCD numbers. Okay, so that means x3 has the weightage of 8, x2 has weightage of 4, x1 has weightage of 2, x0 has a weightage of 1. Right? Now, with this particular configuration, they are saying output y3, y2, y1 are based on OR output. So that means, let us start with a simple case. Let us start with a case of that has least number of inputs. Let us start with y3. So y3 is the OR of what? It is OR of, you have D0, D1 to D8, D9. So you have a D2 here, D3 here, D4 here, D5 here, and so on. So y3 is the OR of what you say D6 or D7 or D8 or D9. That is equal to your y3. Okay. Now, how do you represent it in a short way? You can write it in terms of min terms. That is summation n 6, 7, 8, and 9. This is equal to your y3. Now, similarly, let us try to find out what is our y2, y1, y0. So what is y2? Y2 is summation m d5, 5, 6, 7, 8, and 9. Y1 is summation m 2, 3, 8, and 9. And y0 is summation of m summation of m, that is your 1, 3, 5, 7, and 9. Okay, that's what they mean. They mean to say out as output of OR gate, whose inputs are given by the cross sign. So wherever the cross sign is, that output will be odd. It will be odd. So y3 is OR of D9, D8, D7, D6. Okay, and so on. That is how you get your y3 to B. Okay. So now how are we representing it? It is BCD to decimal decoder. So what is the limit of a BCD to decimal decoder? What is the range of it? Can anyone tell me?
It's up to 9 only, 0 to 9.
Okay, that's correct. So it is 0 to 9, right? So it is 0 to 9. So what is BCD to decimal decoder do is, let us say we have our a simple, let's write this x3, x2, x1, x0. We have suppose all are 0, right? So what will happen is D0 will be high. In this case, the output D0 will be high. Rest all will be 0. Rest all will be 0. If you have 0, 0, 0, 1, the output D1 will be high. Bit D1 will be high, all the other bits will be 0. Okay? It makes sense, right? If you have 0, 0, 1, 0, then the output D2 is high, all the other bits are 0. Okay. So this is the configuration.
Yes.
So now you should find a easy thing you need to find out. You need to find an easy output. So there are many things. You either can have a gray code number, it could be 2421 BCD number, access 3 code, or is it a normal binary number? Is it again becoming like X, like how is Y3, Y2, Y1, Y0 again becoming like X3, X2, X1, X0? Let us check. So we will start with a very simple thing. Let us check in the case for D1. Let us check in the case for D1. D1, what you see, there is only one OR. There's D1 is only one OR, right? It is only one OR, and that is connected to Y0. It is connected to Y0. So now, what would be the output? So we are considering the case of D1. D1 means X0 is 1. So our Y0 is, sorry, our effective Y. Our effective Y is some K3 into Y3 plus K2 into Y2 plus K1 into Y1 plus K0 into Y0. That is what we want to find out. So now, if it is D1, what does it mean? If it is D1, that means our Y is equal to 1. That means our Y is equal to 1. The output is 1. If Y is 1 and D0, sorry, with D1 it is, D1 is connected only to Y0. That means 1 and Y3 is 0, Y2 is 0, Y1 is 0. So Y0 is 1. So 1 is equal to K0. So this means our K0 is 1. Or K0 is 1 in this case. Next case. Let us consider case of D2. Okay, let me use a different color. Case of, sorry, D2. D2 is only connected to Y1. So the Y is equal to, again this K3 into Y3, all that, but it is only connected to Y1. So Y is equal to K1 into Y1. Okay, K1 into Y1. So now we want to see what is the relative magnitude or what is the scaling factor for Y1. So in this case, Y is 2. So K1 is 1. Sorry, K1 into 1 because Y1 will be high. So that means the magnitude of K1 is 2. Okay, magnitude of K1 is 2. Now let's consider for the case of D3. So that means for D3. For D3. In the case of D3, what does it mean? Your Y should be equal to 3. But in the case of this, that is equal to K3 into 0 plus K2 into 0 plus K1 into 1 plus K2 into 1. So that is how much that K1 we found out to be 2 and K0 found out to be 1. So 2 plus 1, that is equal to 3. Okay. So that is verifying that what K1 we got and what K0 we got, that is correct. Okay. So we have got K2, K1 and K0. Now we have to find for the case of D4. Okay, we want to find for Y2. So for Y2, how do we get? Y2 we check for the case of D4. For D4, what is the output? Y is 4. That is equal to K3 into 0 plus K2 into 1 plus K1 into 0 plus K0 into 0. That comes out to be equal to K2. So this implies our K2 is equal to 4. Right? Now only one last thing is left. That is equal to your Y3. This case. Let us consider this case. This case. Okay. If you will see that, that is equal to D0, D1, D2, D3, D4, D5, D6. So it is for D6. For D6, Y equal to 6. That is equal to 1 into your, that is equal to your K3 into 1 plus K2 into 1 plus K1 into 0 plus K0 into 0. So that is K3 is there. So 6 equal to K3 plus 4. So this implies K3 is equal to 2. Okay, so if we write K3, K2, K1, K0, that is equal to 2, 4, 2, 1. Okay, so that is 2, 4, 2, 1. Okay, so that means this entire logic is converting it to 2, 4, 2, 1 BCD number. Any queries in this? Or you want me to repeat? Because this is a very confusing sum. I agree. Hmm. So let me just give a brief run through it. Okay, we have a BCD to decimal decoder. So the what does a BCD to decimal decoder do? It has a number which are scaled by 8, 4, 2, 1, etc. That if your input number, let us say, let's take a simple example. The input number is 6. It means input number is 6. We want to represent the decimal number 6. So if I want to represent decimal number 6, then what will happen? My x3, x2, x1, what will it be? It would be 1, 0, 1, 1, 0. 4 plus 2, 6. Right? So that means this will be on, this will be on. When I have my this number 6, it means what will happen? My D6 bit, that will be high. Okay, let us say D6 bit is high. So what is our D6 bit? D0, D1, D2, D3, D4, D5, D6. That means this bit is high. If this bit is high, means Y3 will be high, Y3 will be high, Y2 will be high. Rest all will be 0 and 0. Okay, rest all will be 0 and 0. So that means my output, if I add Y3 and Y2, it should come out to be 6. So for that, what I did was I gave a scaling factor. We have K3 into Y3, K2 into Y2, K1 into Y1, and K0 into Y0. So in the case of 6, what is there? Y3 is on and Y2 is on. That is 1, 1. Accordingly, I got K3 plus K2. K3 plus K2 should be equal to 6. And I found out. Similarly, I did it for various. I checked for the case where it is only one connection is there. Let us say for D1. So D1 one connection is there that represents only 1. So that means Y0 into 1. So K0 is 1. So in the simpler way, you can get the value of your variables. You need to find what is K3, K2, K1, K0. Okay. All right. So now, mm, okay. So we have this option. Let us check. Let us again. This is like kind of like a true or false. Okay, so we have an even parity checker indicates a parity error for which of the following received data and parity bit. Okay. Hmm. So you let me know. So how many bits are there in the data? Data has 1, 2, 3, 4, 5, 6, 7. So data has 7 bits. Data has 7 bits. So in the case, so data can the parity could be either even or odd. Okay, so in which case is the parity even? So in the case of 1, is the parity even or odd? You tell me. We have many people over here who are very silent and like you to respond. So the case 1, is it even parity or odd parity? So here 7 ones plus 1 parity bit 1. So that means it is even. So your 1 is in even parity. For the second one, what do we have? How many ones do we have in the data? We have 3 ones in the data and parity bit is 0. So it is odd parity. So this is odd parity. Okay. The third case, we have 3 ones in the data but 1 parity bit. So it is even. So that means it is even. Fourth case, it is odd. Odd. Fifth case, 1, 2, 3, 4, 5, 6. So it is even. So it is the fifth case. And in the sixth case, it is 1, 2, 3, 4, 5, 6. Again, it is even. So it is even. So now it says checker indicates a parity error for which configuration. So if it is even, means there is no error. But in the case of it is odd, it means there is an error. Okay. So our correct option is 2 and 4. Okay, so I want you to again look at this question carefully. It is a very simple question, but it has been framed in a way where you could, if you didn't read it properly, you could say that this is the correct option. And you're not wrong in some sense, but in the marks, you will lose the marks. Okay, so that's why I'll again iterate that one of the big enemies for yourself in your exam is silly mistakes. And you should avoid silly mistakes by reading the question very, very carefully. Okay. So now we have 823 priority decoder. These circuits are there. Okay. We have this question. We have to find the correct expression for the outputs considering Q0 is LSB, Q2 is MSB. Okay, we have to find what is our Q0, Q1, Q2 in terms of D7, D6, D5, and so on. Okay, we have to find out in terms of that. So now we have to first find for, let's first try to find for Q2 or Q0. Okay. So we'll first draw the truth table. Okay, let us draw the truth table. We have Q2, Q1, Q0. That means this is 0, 0, 0, and this the D is D0. 0, 0, 1, D1. 0, 1, 0, D2. 0, 1, 1, D3. 1, 0, 0, D4. 1, 0, 1, D5. 1, 1, 0, D6. 1, 1, 1, D7. So what does it? We have to find. So D7 has the highest priority. This has the highest priority. This has the lowest priority. So we have to check the output. Okay, so how do we check this output? So our Q2 is a function of D7, D6, D5, D4, D3, D2, and D1 and D0. Q2 is a function of this. So does anyone remember Shannon's expansion theorem? Hmm? Does anyone remember Shannon's expansion theorem? Okay. So if you want to write Q2 in terms of Shannon's expansion theorem, we'll write Q2 is D7 and f of 1 comma D6 comma dot 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 to D0 plus D7 prime and F of 0 D6 dot 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 D0. Okay, I hope this rings a bell into your to you that this is a important theorem, very useful theorem, Shannon's expansion theorem. So now I want you to tell me the case where we have Q2. Now Q2 is written in terms of D7 and all. So now Q2, D7 and F1 and D6 all that go. So that means you have for D7 you have 1. And we are considering for Q2. That means what this case we are considering D7 case and for Q2 case. So when D7 is high, so D7 is considered and that means Q2 is 1. So what will be your output will be? It will be 1. So this will be D7, sorry, D7 and 1. Now D7 bar, and when you put D7 as 0, right, your output of Q2 will be 0. So that means this will be 0. So that means your Q, no, sorry, didn't write correctly. It is D7 and F of 1 D6 dot dot D0 plus D7 bar when your D7 is 0. Your output will be 0, so it will be 0. D7 bar dash 0. So that means your Q2 will be given by D7 and F of 1 D6 dot 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 D0. Okay. So now what do we do then? In that case, now we can further expand. So right Q2, we can write it D7 and D6 and F of 1 comma 1 dot 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 to D0 plus D6 dash F of 1 comma 0 dot 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 D0. So for D6, what is the case? For D6, again, the case is Q2 is 1. So that means Q2 will be equal to D7 and D6 and F1 comma 1 dot 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 D0 and D6 prime is 0. So that is 0. That means it becomes 0. Okay. So I think I've made a mistake actually. Mm. Okay, I'll get back to you. There's some mistake over here. We have to check it. We mark it cross. There's a mistake here. We'll get back to it. Okay. Okay. We proceed with the next sum. That sum we will get back to it later. So now, what should be the min term expression of the output of the given circuit? So if you see this, your F is a summation of M. Your F is what? I0. It is this I0. This is your I2 bar. And this is your I3, I4, I5. Okay. So now what is your I0 is comes when you, so F is A and B, A bar and B bar and C bar into I0 plus A bar and B bar and C and D bar, because this is for 2, right? No, no. B should be, sorry, it would be A bar and B and C bar, and then the bar of the output D plus I5 is what? 5. So that means A and B bar and C and D. Okay, so this is the overall expression which you should get. Now, F, and this I0 is actually D. Okay, so this can be written as D. So your F, okay, Anup has got the option C, summation of 1, 4, and 11. 1, 4, and 11. No, the option is different actually. So I'll show how it is different. So this is A bar, B bar, and C bar, and D. And this, when you expand, it will become A plus B bar plus C plus D bar plus A and B bar and C and D. Okay, so when you draw the K map, again, we have to draw the K map. You have A, B, C, D, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. You will draw this here, here, here. Okay. So let us say for this number 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so this corresponds to 1. A bar is 0, B bar is 0, C bar is 0, D is 1. Now, let us see for this case. A and B bar, so A and B bar, C and D, so that is 1. This is 1. Now, for the case of A, wherever it is A1 means here, so 1, 2, 3, 4, 1, 2, 3, 4. This is for A. Let us consider case for B bar. B bar, that is this. So B bar is what? 1, 1, 1, 1, 1, 1. So that is for B bar, right? Then for C, it comes out to be 1, 1, 1, 1, 1, all of ones. And D bar, it comes out to be here. This is missed. Let me draw once more. Sorry. Okay. So A bar and B bar and C bar and D. So this is this. So that is comes out to be here. Okay. A bar, B bar, and C bar and D. So this is your 1. Next, you have this configuration, that is your this one. A and B bar. So A and B bar, C and D. So this is your 1. Now we have a configuration of A, where A is 1. A is 1 means this is 1, this is 1. So that would mean this is your 1, 1, 1, 1, 1, 1, 1. Now you have your B bar. B bar is 1, right? So that means B bar, right? B bar is 0, 0. So that means this is also, so this all is already 1. So this is 1, 1, 1, and 1. Okay. Now you have your C. So this is your C. C is 1 means it is this case and this case. So this is 1, 1. Then you have your D bar. D bar is this case. That means D bar is this case, means you have this case and this case. So you have 1 over here. So you have just 1, 0 over here. So that is why your summation of M is actually 0, 1, 2, 3, 4. Only 5 is not there. It is 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Okay, is it clear? Hmm? Okay, so we'll proceed to the next question. This is the question. So we want to find y2. What have they asked? For the given circuit, find out what is the correct option for output y2. Y2 can be PQ prime, PQ bar, P prime, P prime, Q. Okay, let us try to find what is y2. So we have to find what is y2 is the question. Okay. So now y2 is dependent on I1, I3. I2 and I3 it is dependent on, and you have I0 and I1, and you have y1. Okay. So now y1 is D0 bar. Y1 is P bar or Q bar. Hmm. So it is a 2:4 decoder. So you have I1 and I0. Based on I1, I0, you will get a D0, D1, D2, and D3. So Y1 actually is equal to D2 or D0. And this actually is equal to your I3. Now your I2 is equal to your P, right? So D2 will come when your I1 is high, and D0 will come when both are low. Both are low. So that means D2 is actually when you have I1 and I0 bar, and D1, D0 is I1 bar, I0 bar. So that means Y, which is equal to D2 plus D0, that is equal to I1 into I0 bar plus I1 bar and I0 bar. So that is equal to I1 plus I1 bar and I0. So that is equal to I0. Okay. So we got, what did we get? We got our Y1 that is equal to I0, which is equivalent to equal to P bar or Q. Okay, so we got Y1 is P bar plus Q. Now Y2 is not of D5 or not of D7. Now D5 is what? D5 is equal to your I2, I3 and I2 bar, and D7 is equal to I3 and I2. Yeah, correct option. Okay. Thinking Y2 is 0. Let us check. Okay, D5 is I3 and I2 bar. D7 is I3 and I2. So Y2 is what? D5 or D7. That is equal to I3 and I2 bar plus I3 and I2. Sorry. Hmm. Hmm. First, we got D5 and we got D7. Okay, this is clear. D5 is I3 into I2 bar and D7 is I3 and I2. Now, Y2 is what? D5 bar plus D7 bar. So, Y2 is what is D5 bar? That is, we write it somewhere here. Take it down further over here. Okay, we already wrote Y2 is D5 bar plus D7 bar. Now we have to write what is D5. D5 is I3 and I2 bar. I3 and I2 bar plus D7 is I3 and I2. Okay, I3 and I2. So Y2 is I3 bar or I2 plus I3 bar or I2 bar. Okay. So then your Y2 in that case would be I3 bar plus I3 bar is I3 bar. I2 plus I2 bar would be 1. So Y2 should be 1. I think there is some mistake. Not and. What is a? I'm sorry. It is not and. I'm very sorry. So Y2 is actually was there. So Y2 is actually D5 bar and D7 bar. That was the blunder. So D5 bar and D7 bar can be also written as the line over here. Y2 can also be written as D5 or D7 bar, right? D5 or D7 bar. So Y2, what is our D5? D5 is I3 and I2 plus I3 and I2 bar, and D7 is I3 and I2. So Y2 is equal to bar of I3 and I2 bar plus this I3 and I2 bar plus I2. So Y2 is equal to I3 and 1 a bar. So that means your Y2 is equal to I3 bar. And what is your I3? That is just I3. That is just equivalent to your Y1. Achha. Okay, I'm sorry. This is I made so many mistakes. Actually, this is I3 and I3 bar and I2. It's D5, no? So D5 is I3 and I2 bar. So this is I3 and I2. So this would actually be 3 and I2 bar. I3 bar I2. 0, 1. So I3 bar I2. So that is I3 bar I2. So this is I2 into I3 plus I3 bar. So this will be equal to I2 bar. So Y is equal to I2 bar, which is actually Y is equal to P bar. Okay. So this has been a very messy thing which I messed up, but I hope you have understood. Hmm? So we'll proceed. Okay, our time is up for today. So we'll end the session. We'll continue next session with the next week stuff. Okay, so all the best for your assignment. Thank you.